Okay, so go back to share this session with you again. Okay, so this is the outline. This is what I'll try to talk about this for this presentation here. We'll try to go quickly on the precautions to be taken for our safety, the lab guidelines in general, the method to assess you, methods to be used to assess you, and I think I introduced that one at the beginning, type of assignments. But here maybe we can talk about the weight distribution in terms of percentages for each one of them. The guidelines for the report, lab reports, how we need you to write your reports. I'll be talking about this. The resources to be used in terms of software and hardware. And we're going to start talking about, in general, about this logic family, the chips, type of chips, and we're going to use in this lab, inshallah, for the whole experiments. So I'm going to talk in sometimes in details, sometimes I'm going to skip something if it's not necessary, in order just to talk in details about our actual lab. So for the safety, safety precautions here, they are written here in in general way, and usually just to let you know, as electrical engineers, before I'm talking in general here, not step by step what is written here, but as engineers, we should be I mean, aware about the electricity we are using, and when we have to make on, and we have to be aware about the places where we have a push button, emergency stops, push button stops. And once we go in any area to work, you should be familiar with that area before you start working in that area. In terms, as I told you, location for those emergency stop buttons, which type of current you are using in there, the level of that current, if it the type of current or voltage, AC or DC, the level of that one for our cases here, as digital, system course, design course, will be dealing with the maximum 5 volts, 15 volts maximum sometimes, which are nothing. But if you go to a machines lab, for example, you'll be dealing with 480 volts or 450 volts, which is something, of course. So you have to be all the time. Once you go to any place, be familiar with that place, because before you start working in that place. This is just telling you that in general. Um, Here, the guidelines for the lab, they're asking you to come online, sorry, on time. Students should be divided in a group. I think I spoke about that before. Okay, stick with the same group for the whole semester. No need to swap for each lab report. You have to change your partners. This is not allowed, please. The handouts will be uploaded in Blackboard in advance. So I'm going to just review and edit the previous lab reports and make them according to our needs for this semester and upload them there. Okay, students should come prepared for the lab. Yeah, this is very important. That's why we have created those assignments, the pre-labs, because sometimes once we keep, and this is the idea, if we keep that pre-lab within the lab report, for students, they will come to the lab and try to do them. So just to force, and sorry for this word, just to force students to do the pre-lab before, so we call them assignments, and we give a deadline for that, like 2 days, just from our side to be sure that students, they are prepared for the lab, and you know what they have to do, and what they are expected to do to have as results in that experiment. here it was written before that students without preparation will not be accepted in the lab. That was written before, and I changed it to this, that without preparation, and this can be, I can see it, I can feel it once I see the student working. So that student will be, his mark will be affected, and we call that mark in the performance of the students inside the lab. So that grade will be affected if we see that any one of you are not prepared for the lab. Uh, okay, during the experiment itself. What else? This is I'll skip that because they're talking about the components to be responsible for the station itself, the components given to you, the equipment used. Here, before you power on, you have to call us. This is in general, but 15 volts. Uh, it's not something, but still, you can, if you like, you can call me and double check your circuit, and before you power on your station. Go to the next slide. The attendance in the lab is mandatory. Okay, this is general. Those are general restrictions. Now, yeah, this is new. I just copied this one from the website, Qatar University website, just to stick to their restrictions. I don't need to change them, but I change them in a way that this to fit students, not employees in Qatar University. So, according to the policies of this of the state here of Qatar and the university also, we have students should not come if they have those symptoms here, fever, cough, or the shortness in their breath, cycle, something like that. So please, just if you have any symptoms, try to isolate yourself and don't come to the lab. Uh, in the lab, before you go to the lab, I think you are familiar with that. Last semester, okay, we have done this. Our lab technicians, they will be in the front door, and they will check everything. Your ihtiraz should be green. The temperature should be lower than 38 degrees before you come to to enter the lab room itself. So those are some restrictions in general. I'm talking about them. The assessment here. This is the distribution for the weight. It was changed, big changes done, and also a minor one done like at the beginning of this week. Mohammed said he asked me to increase a little bit lab report. It was before 20% and 35% for the final exam, so we increased that to 25%. Practically the lab itself, lab report, it's 30% right now. The 25% will be for the lab report, the report itself, and 5% for the performance in the lab. That's why sometimes, not necessarily in all the times, but sometimes you can see that for the same group, the grades, they are different from partner to partner, and the difference will be this 5% here. The assignments, the homework, the pre-labs, previously called pre-labs, now assignments, will be 10%. The quizzes, as I told you, they will be online, and wait for it is 10%. The mini project, 20%. This will be I have to sit with the Eugene Mohammed said and set a proper one for you. So like as I told you, 3 weeks before we'll announce this, and we can explain the description. We can describe it. I mean, this mini project for you, and you can start working on it. The weight for that is 20%. The final exam, this is a practical one, so it's going to be 30%. Can be half. Okay, once you hear practical, doesn't mean everything will be using mount your circuit and get results. Maybe you have to discuss on paper those results. Maybe you have to on a paper, you have to draw your circuit, complete that circuit before you do it on breadboard and so on. So it's mix of on paper and practical exam.
دكتور
Yeah.
آه، كمان اللي هو الكويزز هتكون بري لاب عن اللاب اللي هندخله لسه، ولا وكمان هيكون من اللاب مانوال، ولا كيف المذاكره من السلايدات ولا من اللاب مانوال؟
Quizzes. This is a good question. I forgot to talk about them. If you go back to Blackboard and you see the the section where I set the schedule for the quizzes, you see all of them. They are like 2 days after the lab. So it means we need, for the quiz, I need to be sure, or we need to be sure that you did the assignment, you understand the part of that subject, you did the experiment, you completed understanding about this subject, and after that you'll be ready to do the quiz. So the quiz is after, not before the subject itself. Okay?
اوكي شكرا.
Yeah.
Doctor.
Yes.
So we will take the lab and before the submission of the lab report, but we already have took the lab, right? So we can do the assignment.
For quiz?
Yes. Yes.
Yeah, a quiz. You have to do the lab. You have the assignment. You have to do the lab, and I think okay. Let's open it here. Sorry, it's here. Schedule. It's coming. Something happening here, or? Will not stop our live because of this internet. So we'll go here. So courses for this semester here, and I think this one here. This is for you. The lab, for example, will be done next week, January 28th, and I presume here that you have started the layout of your lab reports. You come here to do the experiment, take data, and screenshots or something. You can take pictures of your station, and you have 24 hours to submit your report in there. Okay, and after that, you'll be ready to do your first quiz 2 days after the experiment. Okay. We can agree on one thing. I can give you time to do the report like a week, but be sure that you have to understand that topic here and be ready for 2 days after the experiment, because during the experiment you can ask me, I can answer you. And be sure that you'll be ready for the quiz 2 days after the experiment. Yes.
So for the assignments, we have to study the lab before we take the lab, right?
Yes. Yes, sir.
Doctor?
Yeah.
Now about the when we're doing on campus, we will come all, or we will be divided.
Just come the first time and we'll check.
Okay.
We'll check there how we can deal with that. So the first time we are 14 students. We'll check the capacity of our lab, and after that we can decide to divide the groups into 2 sections, 7 and 7, or if you can do everything, if you have, as soon as we respect that social distancing and 1 meter between each other, and I think we can do it in there. As soon as we have this we have met that condition, we can come all of us. But for the time being, the first one here, I need you all to come there and you can check from 12 to 3. Okay.
Victor, when you will divide the groups for the project?
For the project?
Yes.
Look, the groups should be created today or by the end of this weekend. You have to submit your group members. You have to select your group members. And after that, once it's done, this will be for the lab, and I will do the same thing. I will take the same groups for the project. So once you create you select your partners, you stick with those partners for everything. The assignment, if it's a group assignment, for the lab reports, and for the mini project.
اوكي. كمان هنسلمه عن طريق الايميل ولا البلاك بورد؟ لان البلاك بورد مش موجود في الجروبات.
Okay, usually in Blackboard here.
تمام. وهيكون الريبورت هيكون تيم ولا هيكون individually ولازم نكتب الاسامي ولا هيكون بالتيم؟
Please, I think I explained that before. I told you.
It will be teams.
Assignment will be for the time being. For now, the first one we decided to be individual. Okay, we'll decide for the common ones, and they have to discuss with the engineer Mohammed said, because I can take a decision right now, but maybe he will not agree. So we have to agree. We have to synchronize with all students, all groups, mine and his students. This is for the assignment. Now, for the lab report, it should be a group submission, lab report. For the experiment, it will be individual. For the experiment, once you come there, so each one of you, because you remember I told you we have to respect that social distancing between us. So you cannot have like 3 members working in one station and they have 1 meter between each other. That's why the experiment should be done individually. So you come, we'll give you breadboard per person, we'll give you components per person, per student, and you can do your experiment. You collect your data, you collect everything, you go back home and you can meet online with the other members of your group, and you can discuss which one to select as data. We can combine them, you can select a good one, and you can present one report per group. I think it's clear now.
Yes, it's clear.
Yeah. Now for the submission, usually I post like useful in one. I'm going to do like by folders, divide this by folders, and in each folder I'm going to collect any useful information for that subject, the lab report, lab manual for that subject, and the link, submission link for that subject. So right now you have only lab 1. This is your lab manual. After that, I'm going to create link here after this one. But before that, I'm going to create a folder and put this and the link itself inside that folder. Okay. Yeah, this is just to answer a question about the link. There's no link now. Yeah, the link is not there, but it will be created soon, inshallah. Let's go back to here. Yeah, please, all your submissions should be, or submitted lab reports, created lab reports should be PDF version before you submit. Okay, so you can create in Word and submit through. You can convert it to a PDF version. 1 second, please. أيمن ساعة مثلا. I'll call you back. So PDF version, because I need to grade them using my tablet. So convert everything to a PDF version, not Word version, please. It will be electronic. Yeah, my feedback will be on Blackboard. So I'm going to send my feedback, write it there, and submit with the grid, so you can see it in there. Sometimes, and this is a Blackboard problem, once you submit one report per group, the members of the same group, they will see the submission. But once I do my remarks on that, submitted the report, and submit again and upload it in Blackboard, only the one who submitted that report can see my remarks and the feedback. So I'm going to ask any one of you who got like at that time, okay, we'll get that feedback from me, distribute that with or share it with the other member of groups. This is we'll face it later on, and we can fix that later on also. Resources to be used are hardware and software. The software, as I told you, will be using multi-sim, will be using the model sim, and as hardware, we'll be using a kit, different kits. We'll be using breadboards as hardware. We'll be using like we have, and we'll see it after. After we talk about those type of resistors and other components, we see the equipment, physical equipment to be used in Blackboard on campus. I think you're familiar with the resistors here, type of resistors. We have carbon resistors like this with the we call those terminals here. We can solder them using a solder machine and solder them in in PCB board, for example, or we can use them to fix them in breadboard. And we have a ceramic one, ceramic for high power. Those I think minimum quarter watt, 1/4 watts, which is like 0.75 watts. And we have 1 watt maximum, but more watts you go we jump we switch to ceramic ones like this one here. We have surface mount resistors. Those are a type of surface mount. They don't have those legs like these ones here. So we have terminals where you can solder those type of resistors on the breadboard, the surface mount breadboard. Those are type of resistors. I believe you have idea about these ones in circuits 1 and circuits 2. Electronics, for example, you have done fundamental of electronics. So I'll not spend time on talking about this now. TTL family, this is transistor logic family, and those are the type of chips. We have a CMOS families, and for us, we'll be using or dealing with the TTL family. The chips here, the ones will give you physical ones to deal with and work with. They are TTL transistor logic, means just to create one gate, we have 1 million of transistors inside here to create that gate, and or even inverter gate. So those are, the construction of those chips. It's based on the transistor, let's say form or format inside those chips. LEDs, you have an idea about LEDs. We'll be dealing with the 7 segments, and the 7 segments, they are a combination of type of those LEDs inside. So those LEDs, they have like lids. Those lids or terminals. The short one is the cathode one, and the anode is the long one here. Usually you and here students, they refer to that one to positive and negative. So negative is the cathode one and positive is the anode one. And even if it's clear or something like this, you can see inside through this glass, and you see that the cathode has a long part here, and the anode has a short part. So sometimes if you get like a LED with the same length in terms of LEDs here, I mean those leads or terminals, because sometimes we cut them and we use them and we need to reuse them. And once we need to reuse them, we cannot differentiate between them because we cut them before. So what we can do, we can check inside, and inside you can see this big plate here. That's the cathode, and smaller one is the anode. And I think if you can switch to Adobe Acrobat. Yeah. So there, I think you can write in there. Okay, the LED disappeared, but it doesn't matter. I'm going to talk about it here. You see the LED, it's a diode, and the diode has a cathode and anode. The anode, we refer to that as a positive side, and negative side is the other one, the other side. The difference between LED representation, in terms of representation, LED and the diode, is we add like spikes here, just to mention that this is not normal diode, but this is LED. This one will illuminate once we do like high potential here than this side. So this will be having a brightness for it. It can be red, can be, as you saw in the previous one, in here. It can be red, green, blue, can be clear like that. And coming back to this, because I don't have that slide there. So this is one diode, one LED, and so on. If you need to display number 2, for example, we have just to make this one on, this one on, this one, and this one on. And the other ones you send 0 logic to make them off. So by doing this will be on, and this 7 segments will display number 2, decimal 2. We call it 7 segment because it has 7 segments, as you can count them here. 3 in the top, 3 in the bottom, and 1 in the middle makes 7 segments, and 7 LEDs inside. The data sheet of that, and you have to be familiar by using a data sheet for 7 segment, for LED, for transistor, for TTL family, I mean the chips. You have to look for data sheets. The manufacturer for each one of these will give you how you can connect each leg or each terminal, and he can give names and numbers for each terminal, and you can identify them easily by referring to the data sheet of that component. How you can look for a data sheet in internet, in Google? You have to take your components, can be 7 segments, LED, or whatever, and there you see, for example, in one of the sites, you'll find the part number for that component. You type that part number. You can just add as a keyword, any significant word that will help on search or searching for the right component. And in Google, you can find the PDF data sheet, and you can surf through it, and they will show you one example later on. You can check all information you need. You'll find it in that data sheet. It will be given by the manufacturer of that component. Okay, so here we'll talk about this. Yeah, I think I explained that one. I mean, the TTL family, it's used by using like transistors to make those ICs, which is integrated circuit. Okay, integrated circuit chip, and they call it IC. Okay, and from with those ICs, we can have our AND gates, 2 inputs, for example, 3 inputs. we can have an OR gate, we can have NAND gate, we can have NOR gate, and so on. We can have inverter, for example. Inverter, for example, if in our Boolean expression we have like A bar B, for example. So this is the AND gate with the inverted input. So which is that's the AND gate. We need to, we need to do this function AND gate with the between two inputs. So the second one is not inverted direct input, but the other one we have to go through the inverter itself. So we have all the time A and B. That A should be inverted before we give those two inputs to the AND gate, and we can do this expression here, A bar and B and B. So the output will be according to this to those two inputs. So those are the families. Most families will be working with in this course. Here they're giving you different types of those families. Okay, ECL for emitted coupled logic, TTL, which is our case, transistor logic. Okay, we have different other types now. PMOS positive and NMOS for negative families, and so on. You'll be in fundamental of electronics will be familiar with these things here. Sorry. Now this is an example of a TTL family. If they're saying that, sorry, I have 3 back-to-back sessions. As you can see here, I started talking at 9 a.m. and with you now, and I'm going to talk at 3:30. So 3 labs back-to-back. It's a hectic little bit. So I was talking about those families. We have what we call diode logic. Means the inside of the chip, everything will be done using diodes. Some of them, a combination of resistors and transistor, and you call it resistor-transistor logic gates. And some of them using diodes and transistors, and we call them diode transistor logic. Here, for this case, for example, I'm going to go back, erase this. This is that okay? Can you hear me well? And you are
engineer. If you're tired, you can rest for a few minutes or something.
No,
I think that will be better.
I appreciate that. No, I have my water next to me, bottle of water, so I can drink it all. It's okay with me, and thank you for that.
Okay, as you wish. You're welcome.
Thank you. So this is one example. This is AND gate made with the diodes. This truth table. Did you start talking about this in the lecture with the Professor Adil? No, Professor Faisal, sorry.
The AND gates and so on, yes.
Yeah. So truth table for two inputs. All the time, the combination to make from the number of inputs is 2 to the power of that number of inputs. The combinations for our case, for A and B, it will be 2 to the power of 2, which is 4. So we have 4 combinations to be made using those two inputs. We have A and B, and there we can make our combination. Usually we start from right to left. Okay, we have if you have A, B, C, D, like 4 inputs. Once we need to create the table, we create them like this, with the from A to the last one, A, B, C, from left to right. But in terms of weight, it will be from right to left. I will explain more in that one. Okay, let me explain it right now, and I will erase it after. If I need to represent, for example, if I need to know what is this binary number, okay, from base 2, I need to convert this one in base 10, which is decimal number. You know how to do that? I will explain it now. So you put your number as it is, 0, 1. I will make space between those digits, 0, 1, 0, 1. Okay, so this is A, B, C, and D, and I wrote them from left to right, but in terms of weight, it will be from left to right, ABC, but in terms of weight, it will be from right to left side. And we start, look here, this will help you in the lecture also, and will be fine doing this easily. We make 2, 2, 2, and 2 because we are working in binary. Okay, so binary means two, number 2. So we put 2 everywhere. If we have like a train of number of zeros and ones, we write 2 below each one of them, and we start from the right side with the in terms of weight with 0, 1, 1 this side, 2, 3, and so on. If you have more digits, okay, 4, and so on till the last one. Okay, that's so step number 1. Put the 2s below each one of them. Put the power from right to left like this, and calculate them. So 2 to the power of 0 or anything to the power of 0 will be 1, and this one will be 2, will be 4, and will be 8. This one, and so on. Okay, now that's the third step. The fourth one is to multiply this by the number itself. So 1 times 0 will be 0, 2 times 1 will be 2, 4 times 1 will be 4, and 8 times 0 will be 0. The first step is to add them. If you add them, you will end up with number 6. So this one represents 6 in decimal number. Is it clear how you can do that exercise like that?
Yes.
Yeah. Now, talking about this, I come back to my my part here. Now, what we can do, as I told you, we start from lowest weight, which is B, and going toward the heaviest one, which is A. And there we start with 0, 1. We have 4 combinations, so 0, 1, 0, 1. Okay, if you have more, like this case, we have 2 to the power. Let's say, for example, I have only 3 inputs, so 2 to the power of 3 will be 8, so 8 combinations. And we start with the C here, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay, and we count 1, 2, 3, 4, 5, 6, 7, 8. So we don't need anymore the last ones here. So 0, 1, 0, 1, 0, 1, 0, 1, like that all the time. The next one will be 2 zeros, 2 ones, 2 zeros, and so on. So 2 zeros, 2 ones here, 2 zeros for that one, and 2 ones the last one. So 1, 1, 2, 3, 4, 5, 6, 7, 8. The other one will be 4 zeros, 4 ones. Now, okay. So this will be 0. This will be 1. This will be 2. This is 3 decimal number. Okay, and so on, and you end up with 1, 1, 1, which is 8. Sorry, will be 7. Okay, 2. This is 2 to the power of 0, 1, and 2. So it will be 1, 2, and 3. Yeah, right. To the power of no, this will be 4. To the power of 2. 4 plus 2 is 6, plus 1 is 7. So 7. So 3 ones means 7 in decimal. So this is how you can do your truth table. Now, I told you we started with 0, 1, 0, 1, 4 combinations, 0, 0, 1, 1. So that's the first combination, the second one, third one, and the last one here. We come back here and we write we put 0 and 0. Physically or in practice, how we can mimic, how we can use 0 in in practice. 0 means ground. You can make a ground. You can connect our input here to ground. If it's 1 logic, it should be 5 volts DC, which is VCC. So the first combination 0, 0 will be this one to the ground, connected to the ground through wire, this one to the ground, and here we'll be having like, for example, LED connected to ground also, this side. So if this one is 0 and this one is 0, what do you have in the other side? We have, this is a V, which is 5 volts. Okay, let's say this is a small resistor, so 5 volts will be seen here, which is 1 logic, 5 volts. So ground and 5, okay. This represent this like 0 logic and 1 logic, which is VCC and ground here. So the diode, this one will be conducting, since this one, the anode is high potential than the cathode. So this will be conducting, will be like that, wire, and this will be short circuit also because we have a VCC here at the same time. So since they are conducting, this Y, which is the output, which is this node, will be connected to ground. Okay, so for 0, 0, the output Y will be 0, will be ground. If we put here, if we put the next one 0, 1, it means we keep this one to the ground. The other one will be connected to this one here. We cannot, yeah, let's delete everything. This one to the ground, which is 0 logic, and this one to VCC, which is 5 volts. So we'll be having here 0 and 5 volts here. We'll be having 5 volts this side and 5 volts this side. Diode with the 5 volts and 5 volts both sides, or 0 and 0, will be open circuit, not short circuit. So this will be eliminated, this one, but this one will be short circuit because we have 0 and 1, like the previous exercise. So here, this Y will see also ground. So the output here will be 0. If it's the inverse, ground here and 5 volts here will be the same behavior, and the output will be 0 also. Now, if we have both of them 5, 5, which is 1 and 1, those two diodes will be open circuit. Okay, will be open. So open means this way will not see anymore this ground. Okay, because it's open circuit here. What we'll see 5 volts, which is 1. So this will be 1. We'll end up with the AND gate here. Okay, so this represents AND gate. Okay, means both inputs should be 1, 1 to have 1 in here. So 1 and 1. Input 1 and input 2 should be logical 1 and logical 1 to get 1 at the output. The other combinations, whatever you have 1, 0, 0, 1 or 0, 0, the output will be 0. So that's AND gate. Okay, this is just an introduction on those, how this works. Same thing for if you work with resistors or and transistor and diode transistor. Same.
Excuse me?
Yes.
Please, can you repeat what you did on the diagram? How you get it like 0 and 1?
Here?
Yeah.
Or here? The table
No,
or?
no, not the table, the diagram. How you get the numbers?
Okay. Yeah, so we go combination by combination. We start with the 0, 0. And if you remember, the graph or that circuit was like this, and connected to VCC through a resistor. And this is those are the inputs A and B, and the output will be connected here through LED, for example, okay, and ground. So LED to be on, we should have 1 here and 0 the other side. The other side is fixed all the time 0. So here depends on what? Depends on the inputs in here, A and B. For 0, 0, let's do, we'll take more time, another 10 minutes maybe. Just 1 second. So we have this one to be connected to ground to represent 0 logic. This one also to ground to represent the same 0 logic. So I have 0 and 0. Now any diode needs to make in the same direction just to not confusing you. The diode to be conducting means the current will go through it. This anode should be higher potential than the cathode. Okay, so this should be A should be bigger than K in terms of volt. Okay, now if I have 0 logic, means I have ground here and ground here. The other side, the anode, all the time it's connected. This section is fixed. So all the time we have 5 volts here. Look, 5 volts, or let's say 1 logic is better. Why? Because we'll be having a drop in here. We start with 5 volts. Maybe here we'll end up with 4.5 volts. But still, 4.5 volts will be seen as 1 logic for this TTL family. So 1 logic here. So as soon as I see one, I say here 1 logic means 5 volts, okay? Regardless the drop we have here. So here we'll be having 1 and 1 because the same node here. So 1 and 1, 1, 1, or 1, 0 here. 1, 0 means this one will be represented as a short circuit, like this. The diode was before here. Okay, I will not represent that diode, but we have resistor, we have VCC here, and here we have our LED. So LED here will be on or off. We have 0 logic here, and this anode of this LED, okay, this anode will be connected to most highly, let's say, to the ground, not to the VCC, because you have resistor in between. So this will be the same node as ground, right? Is that clear? So this is this is same node.
It will be 1.
This is same node. This is 0. This is ground. One more time. If we take this ground here, because this is 1 node, we'll end up with a circuit like this. Okay, that node, this section here, all this section is 1 node, 1 point. The wire here doesn't have any resistor. So this point, this point, this point, and so on, all along this wire, and this wire, and this wire will be same. So that's the node here. That's the part. Clear?
Yeah, because they are parallel.
Yeah, they are at the same point. The voltage here, if you take voltmeter and you put your probe here, or here, or here, or here, anywhere, they will show the same value, means the same point. It's just extended by wires, and that's it. So this is the so here, this loop here will be having 0 here, will be having like ground. So ground, ground, the LED will be off, and off means zero logic. Clear?
Okay.
Okay. Now let's jump directly to 1 1, because the other combinations, then 0 1 or 1 0, will end up with this one and this one. They will connect our LED all the time to ground. So that means all of these combinations, the LED will be off, which is 0. But if you have 1 and 1, 1 and 1, the diode itself, the diodes, those two diodes, will see one logic here, and we put one logic here also. The VCC, sorry, the VCC here through resistor will be connected to this anode and to this anode, and we need to represent one logic here. Means we take the same VCC and we connect it to this one here and this input here. Okay, so in TTL, and one of the slides later on we'll see that we have a range where I think starting from 3.5 to 5 volts, that TTL, this input, will see all those voltages as one logic. Below that, and I think there is one gap in between 0 and 2.5, I think, TTL will count this one as a 0 logic. So 4.5 volts, because of the drop in here, and 5 volts here, for TTL family, it's same. It's 5 and 5. It's one logic and one logic. And you remember I told you the diode to be conducting, this should be higher than this side. Since both of them, they are similar, so V, let's say V anode minus V cathode will be what? Will be 0, because they have 5 minus 5, 0 volts. So 0 volt means nothing in here. It can be represented by open circuit. Even if this side is connected to VCC and the other side through resistor, and here the Y, which is the anode, the LED, this all the time 0. So this is open circuit. So what we'll see 4.5 volts in this side. 4.5 volts and minus 0 will be 4.5, which is this should be on. Is that clear?
Yes.
Okay. So now let's go back to continue our discussion in here.
But Engineer, I have a question on this on the whiteboard.
Yes.
If the cathode is from 3.5 till 5, it will read it as one logic gate, right?
Yes.
But why 3.5? Is it shouldn't the anode be more in order to be short circuit?
We're not talking about physical diode in here, but you know, if you have chance to look in YouTube's, for example, how TTL family or all ICs, they are constructed. You see inside, you know, something like only holes everywhere. Okay, but we represent these ones as diode. Okay, so the diode to be conducting, just this one to be higher than the other side, regardless if it's 2 volt and 1 volt here, it will be conducting the diode. But if you put 1 and 2, it will be blocked. 2 and 2 or 1 and 1, it will be blocked also. But as soon as this side is higher than the other side, it will be conducting.
Is it because of the voltage drop across the diode?
Which voltage drop?
Because we learned in fundamentals that across the diode there will be 0.7, and it varies from diode to another, from diode to another. So we learned that most of the diodes they get 0.7 voltage drop across them. So is that the explanation why We don't have to get 5 exactly.
No, I'm going to answer differently because you went far away a little bit. But look, the diode in general, that's let's say electrical symbol for the diode, but inside it has like a small battery like this, okay, and you know, and that's the diode like that. Now, once you use the physical diode, the real one you have, that diode here will be conducting once this V input bigger than this, the internal voltage, and we call this one a threshold value, a voltage value. You remember in the fundamental of electronics, it has like a characteristic like this. So if you make a tangent, so this is 0.7 you're talking about. After 0.7, that diode will be conducted. Below that, it will be blocked. Okay, and from if it's
Okay.
as you have said, then from family to family, this value will change. Can be 1.2, can be either 0.2 also volts. Okay, and this is for the diode. But for our case, it's different. It's IC. We talk about diode just to I mean explain and how it works inside this TTL family. But keep in mind that your IC has let's say 7 legs or terminals from this side and 7 from the other side. And for example, this one represents the AND gate like this. We have 2 inputs and 1 output this side. So this A, B, and C. Usually what we do, maybe I'm going far away again from your question, but once I will answer this question or explain this part, you can connect your question to my answer. For the TTL family, for example, I'm using like in my equation or my application in general, I need just to use let's say for NAND gates. If I don't have in my lab, I don't have something else, only I have a NAND gate. I can do that. Sorry, I go. Yeah, NAND gate like that, and I need to do A bar. So I can do this A bar. A bar, we should have the inverter, another IC, and they call it inverter, where we have only inverters inside. 1 in, 1 out. Here we have NAND gate, and this is one of the exercises will be done later on in using the next experiments. If we need we have only a NAND gate, and we need to create this inverter or invert our input, still we can connect our input A to this input here. It will be inverted through this NAND gate, but we have to take care about this input here, because as I told you, TTL family will count 0 to 2.3. I don't know why my pen is using or tablet is using that. 2.3 volts. It will be counted 0 logic, but suddenly if this one goes up to 3 volts and above, this will be seen as 1 logic. If we keep this one floating like that. And this will be working as AND gate, not inverted gate. You'll be having A and B bar in this side. But if you need to avoid having this situation and work as with NAND gate as inverted logic gate, you have absolutely to force this one to be 0 logic all the time. So you connect this one to ground. So by connecting this to ground, I'll be sure that I have all the time E bar this side. This will not affect my 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 circuit. I don't know if
Okay, thank you, Doctor.
Yeah. If you go back here, I think your question started from this part here, maybe, because I have 5 volts here, and we have 4.5 volts. No, just to answer differently to your question, imagine this one has this VF, the forward voltage equals 0. Okay, so there is no battery inside. It's direct diode. If this one is bigger than that one with a certain value, so it will be conducting. I mean by one here, the anode and cathode, and vice versa. If they have the same polarity, 0, 0, I mean same level of voltage, 0, 0, or 5, 5, or even 5, 4.5, or 4.5 here and 5 the other side, they will be blocked. They will be represented as open circuits. Let's go to the next slides, and for the coming ones, I'm going to jump some of them. I think you're familiar using those breadboards. You have used them in circuits 1, circuits 2, and fundamental of electronics. And even though here I posted one document, especially on how to use or deal with the breadboards. For some of you, if this is the first time, you can open this document and you can check how you can work with the breadboard. I'm going to skip this. Those are tools to be used in it, in terms of wires, and those tools, the pliers to use in order to, remove the isolation from each part of this wire and use it. Those are tools to be used in the lab. Those are the equipment I was talking about at the beginning. We have different ones. For our first experiments, we'll be dealing with this part where we can represent the inputs using those switches. I don't know if you can see them. Those are switches, up and down, up and down. You can, and they are connected to ground the other side, so you can make 1 or 0, 1, 0, and so on. The output will be those LEDs here. Depends on number of outputs we need. And your breadboard, on the breadboard, you can fix your IC, and you can connect the inputs to the terminals of this IC to the inputs, and the terminals which represents output for that gate to the LED here. We'll be working with that, inshallah, during the semester. This is another type of a kit. They have the same thing. I think the one who took a picture for that, we have switches down here, and those are the outputs. Those are multimeters. I'm going to skip, how to work with multimeters. And here they're talking about those families. Okay, not spend more time on this. You have this slide. You can go through it. This is a very important part in here. Let's go back to here. Yeah. Sorry. Now, if you have a IC, it's like a diode. Okay, diode. How you can identify the diode or a transistor? Transistor has, a collector, emitter, and base. Okay, so 3 legs. They are you can identify them easily using datasheet. For this one, it has it's a black chip like this. There is no name on them, no numbers. But how easily you can identify numbers? By using this notch here, or this hole, this dot here, the black one. So for this, we have 2 examples. We have this example with the notch. Even if you see that hole, you can ignore that. but if you have both of them, you have to refer to the notch itself here. This one here. So you face that notch to you, and you count from left to right in counterclockwise direction. You count 1 and so on, 1, 2, 3, 4 to the last one. For this case, we have 7 terminals this side, and you continue here. Don't jump to that side and come back. You don't do this. You continue counterclockwise. It's like your clock, but the other direction. Okay, the clock goes this direction here to count the minutes or seconds. The other, for our case, we do the reverse of that one. We go from that side and count 1, 2, 3, 4, 7, and continue from this side 8, 9, 10 to the last one. If we cannot see this notch, like this one, you can see identify in one of the corners this hole or this circle, this black one, and from there you can count. This is your 1, 2, 3, 4. You continue here. This is 5, 6, 7, and 8. This is how you can identify those terminals. And now, taking this reference here, part number, especially TLC555CP, you write this one in Google, and you will get data sheet. The data sheet, which is something like this one. So this is one of the data sheets. You can go in. You can not necessarily in ON semiconductor or Fairchild semiconductor website or TI. You can just type in general in Google the part number you need, and you will get that data sheet. And there you can see exactly what is 1 for our case. And if you can zoom here, you can see this is pin number 1, 2, 3, 4, 7, and so on. Now they identify each gate by the number. You see number 1, 1, 1. This is one gate. Means those 3 terminals, they represent one gate. And now this gate has A and B, means has 2 inputs, and Y, this is output. Those are inputs, and this is input. What is inside? This is one of our exercises for this lab. Today's lab, we'll give you chips, and you can identify them by just putting 0, 1, 0, 0 combinations in here in those inputs, and collect the outputs. And through this truth table, you can create your Boolean expression, and you can identify if it's AND, or NAND, or any other type of gates. Here we have, this one has one gate, another gate here represented by number 2. Okay, another one by number 3, and you see those are the inputs. This is the output. This input. This is output. This is so we have four gates inside this chip. Usually we deal with this type of chip, not this one here. This one for advanced, applications, where we use them on a PCB board. Sorry.
Doctor?
Yes.
Please, how you know the inputs and the outputs?
Here, A, B, and Y.
Yeah, so the Y, it represents the output always.
Yes. If you see, for example, 1A, 1B, 1C, and 1Y, means this gate has 3 inputs and 1 output. Okay. If you see A and Y, means this gate has 1 input and 1 output. Okay.
Okay.
Yeah. Now let's go back here. It's very important to understand this part, the part number of each gate. Usually you find SN, for example, and this is like can be NI, which identifies the national instrument. For example, this is the company, the name of the company. sorry, it can be different from company to company. This is the family type. Usually for our case, we work with this family, 74 family. Can be 7400, 7401, 08, 02, 21. It depends, okay? So 74, this is the family used. Sorry. The two next digits after those letters, sometimes you don't have the letters. We have just after the family, we have those digits here. They identify the gate type, NAND or AND or XOR or any different type of those gates. This is just the type of the chip and its package. Remember the previous slide we had something like this, and the other one which is squared. And this last one tells you if it's this part or this part. Especially we need to know this once we need to buy from websites any of the chips. We have to be careful because not just buy like that, because in our application we are waiting to get something like this. But suddenly, once we get through this DHL or any type of delivery companies, we get the chips with this. Should not be surprised because you didn't take or pay attention to this part here from their website. And N, it's like a dip switch. Sorry, not dip switch, but dip IC. Dip IC means with the terminals like that. And we have another type which is the surface mount type. This will come with experience, once you do more exercise, more practical experiments, you can understand this more and how you can select the type of chip. Here I'll skip these ones, and this is part of your exercise, but I think I went through this many times during the previous slides. You see here you have for each gate you have the identifier for this gate. This is inverter, and they usually call it Schmidt or something. It depends on the data sheet. Thus the inverter has one input and one output, so you find it A and Y, for example, for each one of them. One A, one Y, 2A, 2Y. This is a number of the pin, but not the number of the gate itself, the input.
Please, doctor.
Yes.
About the VCC, it represents to what exactly?
Yeah, it's like your car. You have all options in your car. If you don't put gas for your car, you cannot start it. You cannot run with that car. Same thing for here. All chips, you have to feed them. You have to put your 15. It depends on the chip. It depends on data sheet, but most of the time it's like between 5 and 15 volts, and you have to ground them. So most of the time 14 and number 7 represents ground and VCC. You have absolutely to feed them before you can use them. Okay, for all chips.
Okay.
Yeah.
It's like a battery, يعني?
Like what? Sorry.
Like a battery.
Not battery. No, not a battery. It's
or a power. Or...
No, you can. I don't know. Maybe if you meant like you have to use a battery to feed this. Yes, you can do it. The problem is the battery has certain time of charge and discharge, and it will be done. So your circuit will not work for a long time. But usually, what we do supply in here. We use like our DC power supply, and that DC power supply has two terminals, plus and minus. Plus will be here, and minus will be in here. And this one can be 12 volts, can be 15 volts, can be adjustable one. You can adjust it to the value you need or according to data sheet. If you remember, in data sheet for each component, they're given V supply, and we refer to that one to VCC, and they give you a range that to supply this type of IC, you can supply it between, for example, let's say 5 volts and maximum 18 volts. So anything in between will be fine with those chips to work. So this will be also by experience. As soon as you work with them, you can understand how you can use them. But now, for all experiments, be sure that any circuit you wired inside on your breadboard, you should feed it first. You should give it plus and minus 15 volts, for example, before you use the gates from that that chip. And yeah, here it shows exactly the level of for this TTL, for example, family. It shows the levels here. For the input will be counted as high or 1 logic between 2.5, not 3.5, 2.5 and 5, and low logic, which is 0 logic, between 0 and 1 volt. Okay, the output will be on between 3 and or 2 and 5 and 5, and same thing almost, 0 and 0.5 as low logic, which is 0 logic. I talked about this. This is just one exercise how you can wire. If you have like I don't know, they're not given here. They're not given. I mean the equation, but if you have most in theory, yeah, it mentions here in theory. You will, in your lectures, you will be familiar with that more. But for example, if I have, according to this exercise, I have AC and same input here to be wired. So same input. I have three inputs, A, B, C, and C. This is A will be given to this gate, and given to this gate also. And C will be given to this input, and B to that input. So after, here we'll be having A bar, and here we'll be having C. So this is AND gate. We'll end up here with A bar and C. Here we have A. We have direct A. It's not inverted one, but we have inverted B input. So here we'll be having A and B bar or B not. It depends on the lecture how you can name it. Usually in my labs we call them bars. So E bar and B bar. Here this is OR. So F, which is the output, will be E bar C or A B bar. Okay. And how you can wire them? You can take a wire from switch A, for example. You can select one of the switches and you can name it A. So from the switch, you come back to you wire it directly to one of the chips that you have, like this one here down. E will be wired directly to input of that chip, the inverter. The output of that chip will be given to AND gate. That's why if you load that line, will be going to one input of this NAND gate. Yeah, this is another exercise here. This one, not that one, but this one is different, okay, than this one here. Here we are using NAND gates. But there is no OR gate here. So it will be given to NAND gate. We have a C. So we can select your input C to be given directly to this NAND gate, the same one. The output of that inverted, this NAND gate, will be given to another NAND gate. That's why we take this input, this output. You can select whatever once, not use it once. You can select them, and you can put the output of this to the input of the next one. Okay, same thing for this side, this part. You can use, I mean, the same. We have A, so we can take the A directly to a NAND gate. You have to invert B before you come to this NAND gate. Okay, the output will be given to the same selected NAND gate here. Okay, and the output of that NAND gate, the last one, will be your output, final output. This should be wired to LED just to check on and off or your function in here. Okay. Both of those switch or those ICs, they are powered, okay, through 5 volts, for example, for this case, okay, 14 to 5 and 14 to 5 volts and 7 to ground. So both of 7s here, they are grounded, and both of VCC or 14 can be connected to the same VCC. Thank you, guys. I'll stop it here just to prepare myself for the next lab 3:30. Before I leave you. I'm going to open. Now this is the same as the one I was talking about. I'm going to go back here and open this lab manual. Yeah, in the lab manual, I think, yeah, it's not the one I need to post for you because I edited that one, so I'm going to post the last version. We need you to use multisim. Okay, so in multisim, let's open multisim. Last few minutes with you, please. I know we still have another 1 hour, but I'll ask you your permission just to stop it here after 5 minutes from now. Now you go to you place a component. You know, we have different places from where you can add components in here. You have a place menu and components there. Or what you can do, you can right click in your working area, right click, you get this pop-up window there. You have a place component. So in place component, I think you can go to if you drop that list here, go to TTL. Yeah, you see TTL family. So there we have gate by gate, or if you go a little bit down here, I think you can get the chips themselves. Okay, just pick this one here, for example. By the way, in the lab manual, she's this one. They're giving you the part numbers. So you go to here and you select, for example, I don't know, 74LS02, 74LS02D, which is the one. And by chance, I'm here. You can select any one. This is only the gate, but this is the chip. You take the IC, which is a chip, the IC. You add it to your working area. Now, what we need the switches to represent the inputs. You go back here to, I think in sources, you can find them here in sources. And there you have digital sources. So in digital sources, I'll ask you to select this one, which is interactive. While your simulation is running, you can change this constant between 0 and 1. So I'm going to grab this. Okay, I can add more in here. Now we need the output. Yeah, we need.
Why don't we use logism instead of multism?
What do you need to use? Sorry.
Logism.
Which one is it? I didn't get your comment. Sorry. Where? Tell me where. Instead of what?
I think he's talking about another software. He said it's called Logism.
Look, I don't need to go this way because not all of you are familiar with that one, that software. So what I can tell you, you can use whatever you are familiar with. The problem is I don't have it. So if you need
sorry, my battery died. I meant there is another software called Logism.
Yeah, this is what your partner, your colleague explained to me. Look, I don't have it, but if you send your file to be verified, I cannot verify. I don't have it. I'm going to stick with this multi-sim. So you can use it, no problem. But as I told you,
I think it's easier to use it than Multism.
yeah, go ahead.
It's all about logic gates and this stuff.
Yeah, look, I will not stop you to use that one. Just use it. If time comes to verify your file, I'll be forced to to look for that software and install it in my laptop in order to verify your work. But anyways, now I'm going to continue on that multi-sim. I told you we have inputs can be those from sources library and digital library also sources. You can select all inputs through this interactive digital constant. The output will be through those indicators here. So indicator you have lamps, for example, and you have different, sorry, not lamps, a probe, and the probe you have different ones with different colors. Yes, sir.
Gene, I didn't understand what the previous block, the interactive constant.
Yeah.
What are we going to use it for?
Yeah, I will explain it as soon as I collect only this one here.
Sorry for it.
No problem. And now you remember you have two inputs, for example, A and B in your table, through table, and you have Y as output. So this is A. That can be this can be A, for example, the input A, and the other one will be B, for example. Okay. So I don't know which type of this part here. So we can collect. You see here 1Y, 1A, 1B. I don't know if it's clear. Cannot zoom. Yeah, I can zoom maybe. Yeah, I can zoom. Look, we have 1Y, 1A, 1B. Means those are the two inputs, A and B, and the output is the one at the top here. What I will do, I'll take my inputs and connect, for example, A to 1A and B to 1B, and the output will be verified in here. That's it. Of course, we need to supply this, as I told you. So we'll go back to library, and from there, from sources, I'm going to take this power source. There we have VCC. Okay, we come back here. We'll take this digital ground, so we can ground our. We can supply our TTL chip. Now I think once we start this, which I have it in here because of that recording window, that's why I couldn't see that start here run button. So I run this one. This type of switch has 1 but we have 0 output. Interactive, now I'm answering your question. What we do with this, we can change the combinations 0, 0, 1, 1, 1, 0, and so on. So if I put this one, click on it, while this is running, this will accept this change. So I have 0 and 1, it keeps giving me 0 as output. 0, 0, it gives me 1 as output, and 1, 0, it gives 0. So this is NAND gate. Once you do your truth table, and you can take the equation from there, that Boolean expression will end up, but this represents NAND gate, and so on. So that's the part of your exercise, your lab report. We're giving you those chips here. We call them ABC. So identified here, A should be that one. So you select this, and you come back to A, and you see you have where is it? We have A and B as input and F as output, and there you have A, B, and Y. So you connect your inputs here and grab or collect the outputs, and you can identify which type of IC is that one. You can add one column here after in your report. You can type name, for example, or IC name. Okay, and there you can name it. For this one, we found it to be NAND gate. Okay, so we need you to do the same thing for the other ones here given to you. You go one by one your simulation, and you have to take a screenshot of your simulations. Taking screenshot, you have, I think, once you stop this one, so you can select this like that, Control C, and in Word. This is in the same page here. You can make Control V, and you will get exactly your figure like that. Okay, proper way and clean net, and you can use it instead of screenshot and crop and things like that. Okay, but to do it, you have to stop your simulation. If it's still running, it will not. The Control C will not work. Yeah, we'll go back here. So chip by chip, you have to identify them. It is guidelines and how you can do this. As I told you, this is a previous, this is old one. I'm going to change it. I removed this part and I put it as a breadboard document in there. So this part, I minimized my lab manual. This is the working sheet, the answer sheet. There you type your name. This is the one you have to submit for us. Type your names as a group. And yeah, 1 second. Just to be more clear again, let's skip that one. This is done by Engineer Mohammed Sayed. For my case, I updated that one, lab 1. I don't know why I posted that, the previous one. Yeah, this is the one here. This is the one that you should have. Okay, this is a new layout. I changed most of the thing. I removed that thing related to breadboards because I separated them. It's just appendix how to work with that thing, the breadboard itself. Now I think still this is not the one I want because the one that one is here. Okay, I'm going to update it properly, but let's go back to the one I was in it, which is this one here. I continue here. Yeah, here I created I divided our work into 2 sections and I called them exercise 1. Exercise 1, you have to put your truth table here, use that chip in multisim and write your Boolean expression here, give the name and copy paste the part number from that table in here, and you do for all of these things here, all those ICs. The other exercise, I'm asking you for universality. I need you to use all of them using NAND and all of them using NOR. This is another exercise to be done. So you can change AND gate using NAND, using NOR, and so on. OR gate using NAND and using NOR, and so on. So 2 exercises to create your lab report.
Please, Doctor,
Yes.
about the exercise 2, could you repeat what is the target?
Yes, 1 second.
No problem.
E and V. This is this configuration here. The output is there. If we put 2 bars, we're done. Okay, we can use 2 inputs, A and B, and can be sent through the first NAND gate. So here we'll be having A and B bar, and the second bar, the one in the one here, the second one will be going through another NAND gate. Since it has 2 inputs, so we'll put that one here, and this will be A and B 2 bars. So you see, and if you simplify this, you'll end up with A and B. If you have only if you have AND gates, you need only 1 gate to do that. If you don't have AND gate, you have NAND gate, you should use 2 NAND gates to do this AND gate here. Thank you, guys. This is an explanation how you can use this. This exercise here, and I mean logic gates in general. I'm going to stop here. I gave to myself a break of half an hour. I see my voice is completely gone. So